Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll explore performance testing for matrix multiplication, specifically focusing on parallel computing at the single CPU core level. We'll analyze optimization reports generated by the Fortran compiler and discuss loop vectorization. The compiler's automatic vectorization capability utilizes single instruction on multiple data (SIMD) to parallelize operations across multiple data elements. I've developed a Python script dedicated solely to compilation tasks. As you're likely becoming more familiar with these scripts, I'll keep the details brief. We're using the same compilation options that yielded optimal performance in our previous video. Additionally, we've included an option for the compiler to generate an optimization report. I've also provided the Linux commands for loading the latest Intel Fortran compiler, iFort. Before compiling our program, we need to switch to a compute node using our Python script. It's essential to compile the Fortran program on the same type of nodes used for computing. We'll begin by using this script to generate an optimization report for the Fortran program MXM, which produced the best performance results. Compiling on login nodes might cause issues because they might have a different architecture than the compute nodes. This could lead to unexpected outcomes when running the program on compute nodes, especially if they require specific architectures, like GPUs. It's therefore not advisable to compile on the login node and then execute on some of the compute nodes. Compiling and executing should be done on the same node. After executing the ll command, we can see that the compiler has produced an optimization report. Let's open the report using the Emacs editor to examine its contents. Feel free to make notes on any significant findings inside the report. In the optimization report, there's a reference to an Intel web page discussing vectorization and optimization. As we scroll through the optimization report, we reach the section discussing the first loop in the program at line 15. This loop initializes the matrices. Here, the compiler has executed a loop interchange. The loop interchange performed by the compiler switches the order of the loops, making the J loop the outermost instead of the I loop as written in the program. This step is crucial for enabling loop vectorization. As we proceed further down the optimization report, we reach the crucial loop at line 24. This triple-nested loop handles the matrix multiplication process. Once again, we observe the loop interchange. The compiler selects the J loop as the outer loop and the I loop as the inner loop, deviating from our program's original structure. This adjustment is vital for facilitating loop vectorization, and we can see that the permuted loop has been successfully vectorized. We'll provide a more detailed explanation of vectorization shortly. Now, let's examine the optimization report for the Fortran program that utilized the variable TMP in matrix multiplication. Once again, we compile this on one compute node. After executing the ll command, we can see that the compiler has produced an optimization report. Let's open the report using the Emacs editor. The optimization report indicates that the compiler performed loop interchange and vectorization on the first loop, responsible for initializing the matrices. Consequently, this loop has been optimized in a similar manner as the program without the TMP variable. Looking at the loop responsible for matrix multiplication, we observe that the compiler did not perform any loop interchange. Additionally, there are no reports of vectorization for permuted loops. This lack of optimization explains the program's low performance, achieving less than 1 gigaflops per second. Examining the loop for matrix multiplication with the loop interchange, we find that the I loop has become the innermost loop. Additionally, the I index corresponds to the first index in C and A, while the J index is in the outermost loop and represents the last index in C and B. When setting J equal to 1 and K equal to 1, we perform a vector calculation in the I loop. The value of n determines the length of these vectors, which in our last test was 4096. The vectors C and A consist of 64 bits real numbers, and identical instructions are applied to these vectors. These instructions can be combined into a single instruction known as FMA. This FMA instruction needs to be applied to 4096 real numbers in the I loop for every J and K. This process is a single instruction on multiple data, SIMD. FMA, short for fuse multiply add, combines a multiplication and addition into one operation, typically used with floating point numbers. The vector register can input multiple real numbers into the CMD process. AVX 512, with its 512-bit capacity, can input 8 real numbers of 64 bits each into the CMD process. As a result, CPU cores can conduct parallel computing using AVX and SIMD and perform operations on 8 numbers in parallel. In our previous video, we examined the test with n equal to 4096 and noted a doubling in performance from about 6 to 12 gigaflops per second upon including the march option. This improvement happens because without the march option, the compiler assumes a 256-bit capacity for the vector register, limiting the CPU core to performing operations on only 4 numbers in parallel. With the Skylake architecture specification, this is adjusted to a 512-bit capacity, allowing the CPU core to perform operations on 8 numbers in parallel. I've revised our testing Python script, incorporating the compiling option we utilized in our previous video to achieve optimal performance. As mentioned earlier, we discussed in our initial video that the march option requires knowledge of your Linux system's architecture. However, I'd like to demonstrate that the xhost option can be employed when architecture information is unknown. Let's explore additional compiling options to enhance performance. One option worth testing is Inter-Procedural Optimizations, IPO. This is a collection of compiler optimizations that examine and optimize code across multiple procedures or functions within a program. Unlike typical optimizations that concentrate on individual functions or loops, IPO looks at how different parts of the program interact and depend on each other, enabling more comprehensive and effective optimizations. We can also try the mat-mul option, which identifies a matrix multiplication routine in the Fortran program and swaps it with a highly optimized routine from the Intel Fortran compiler. This isn't the same as the intrinsic function mat-mul in the Fortran programming language. In our previous video, we observed that using this intrinsic function only matched the performance of matrix multiplication using the nested loop. When running the Python script on a compute node, we observe that the options we utilized in our previous video still yield a performance of approximately 12 gigaflops per second. We notice that the X-host option achieved similar performance as employing the march option. We observe that the IOP option increases the performance to about 17 gigaflops per second, but the matmul option achieves the best results. The highly optimized routine from the Intel Fortran compiler boosts performance to around 36 gigaflops per second, which is about 3 times higher than in our last video. This performance was measured during a wall time of about 4 seconds. Let's reevaluate this by increasing the problem size, setting n equal to 8192. As we scale up the matrix dimensions to 8192, we need to adjust our memory allocation accordingly. In our previous video, we demonstrated that the memory usage with n equal to 4096 was about 388 megabytes. Therefore, we can estimate that the memory usage will be 4 times larger with 8192. Let's request 2 gigabytes of memory and update our setup Python script accordingly. I've also provided the Linux commands for loading the latest Intel Fortran compiler in our setup Python script. We must remember to update n to 8192 in the Fortran program mxm. We must also update the testing Python script with n equal to 8192. As we scaled up the matrices, we observed a proportional increase in wall time, approximately 8 times longer. This outcome is expected, given that matrix multiplication involves a triple-nested loop. Despite the longer runtime, the performance remained steady at around 12 gigaflops. However, we encountered a discrepancy in the performance when using the IPO option, which dropped from about 17 to 12 gigaflops. Interestingly, combining the matmul option with IPO yielded a performance boost, reaching approximately 44 gigaflops per second. Let's further explore the performance implications of the IPO option. By running the Python testing script with different IPO settings, we can gain a better understanding of its impact. Notably, we observe that while the matmul option consistently delivers high performance, it doesn't depend on IPO to maintain its efficiency. Achieving approximately 45 gigaflops per second, this performance level likely represents close to the maximum achievable performance on a single CPU core. It might be interesting to examine the optimization report with the matmul option. We can accomplish this by once again compiling as we did previously and reviewing the report. In the report, we observe that the loop for matrix multiplication has been substituted with the matmul intrinsic. However, it's crucial to clarify that this isn't the intrinsic function that comes with the Fortran language. Rather, it's a highly optimized routine provided by the Intel Fortran compiler. Let's estimate the theoretical maximum performance for one CPU core on the Skylake AVX 512 architecture. Each AVX 512 FMA unit can process 8 real numbers of 64 bits each in the SIMD process and execute one FMA instruction for each real number. Since one FMA comprises 2 instructions, this results in 16 flops. Given that there are 2 AVX 512 FMA units on one CPU core, the total performance per clock cycle becomes 32 flops. The Intel Xeon Gold 6138 processor has a base frequency of 2 GHz, allowing for a theoretical maximum performance of 64 gigaflops per second. On the other hand, the Intel Xeon Gold 6230R offers slightly higher performance with a base frequency of 2.1 GHz. It's important to note that the base frequency can vary due to factors such as performance optimization, power efficiency, and thermal management in different operating conditions. In this video, we've explored parallel computing on a single CPU core, while the next logical progression would be parallel computing on multiple CPU cores. Our upcoming video will look into parallel computing on a single GPU. Join us as we discuss GPU offloading in our next video. I am looking forward to the next video, wishing you all happy computing in the meantime.